Okay, so we're going to continue on now, talk a little bit about molar mass and Avogadro's number. And these are two really important sort of calculations or conversion factors, really is what they are. Really, molar mass, which has units of grams per mole, and Avogadro's number represents obviously a certain amount of something, are two values that we do use occasionally here in chemistry. Really, out of the two, molar mass is used a lot more than Avogadro's number. But we'll talk about them both. So it really all starts with the idea of a mole. And when we talk about a mole, not the furry guy, but it does represent a certain amount of something. So in life, we have a lot of words that we use that represent an actual value. So if we say we have a pair of shoes, that means we have 2 shoes. If we say we got a dozen roses, we got 12. Or if you were old enough, they used to say a gross of pencils, like 144 came in a gross. I don't think they even give pencils out anymore in school. So when we talk about the mole in chemistry, it does represent a certain amount of something. So a couple important things. The mole needs to be abbreviated, and this is the abbreviation here. So when you see MOL, that is the abbreviation for mole. Had to cut off something, so they cut the E off. It is not molecule. So that's a very common mistake that people will make. They'll see MOL, they'll automatically sort of think molecules, but it is the abbreviation for a mole. And as we will see, 1 mole of pretty much anything will equal 6.022 times 10 to the 23. And the units here can really vary depending on what you are dealing with. It can be atoms if you're dealing with atoms. They can be molecules if you're dealing with molecules. They could be particles. They could be pizzas. They could be shoes, whatever they may be. Probably most often in chemistry, without the occasional pizza that pops up, atoms and molecules are most likely your most common unit that you'll use. And they do sort of are interchangeable, the units that go with that number. That number, as we will see here in a second, that is what is referred to as I can say avocado, Avogadro's, there we go, number. I had a girl, she always said avocado, and she got me like saying it towards the end. So that's Avogadro's number, which is really sort of like a constant number. So it's a constant value that you sort of always have if you need to use Avogadro's number. So let's take a look at that here. We'll come back to those pictures in just a second. So Avogadro's number, that is the real number, but everybody does use the 6.022 times 10 to the 23. Also, obviously, really important to make sure that you use your exponent button when you use that in your calculator, like we talked about. But really, Avogadro's number is a conversion factor, and it is the conversion factor that allows you to go between moles and either atoms or molecules in most cases. Or go backwards. If you're starting with atoms or molecules, you can use Avogadro's number basically to take you back. So if you have moles, you would times it by Avogadro's number. That would give you atoms per mole. The moles would cancel, leaves you with atoms or molecules. If you are starting with atoms or molecules, you would divide by Avogadro's number. 6.022 times 10 to the 23 atoms per mole. Atoms will cancel, leaves you with moles. So again here, depending on sort of which way you're going, you're either going to be multiplying by Avogadro's number or dividing by Avogadro's number. Now, sometimes people learn Avogadro's number and they want to use it in like every calculation they ever do, and you should not do that. That's maybe another very common mistake that people will make. They go like, I learned this number, let me just throw it in there because, you know, it sounds more chemistry like if I use Avogadro's number. And you shouldn't do that. So how you know if you need to use Avogadro's number is pretty straightforward. Either you have a number that is in the units of atoms or molecules, or you're asked to solve for something in atoms or molecules. there's no mention of atoms or molecules, you should not be using Avogadro's number in that calculation. So it is sometimes overused and used in the wrong spot or wrong way. And that's, again, a very common mistake. So those are the keywords that you're looking for in a problem: atoms, molecules. Either I need to solve for it, or I'm given a number, and that means somewhere along the way, Avogadro's number should come into play. Again, if you do not see any of those, then you should not use Avogadro's number. Now, we could use Avogadro's number in a couple of different ways. We could take anybody from the periodic table. So, for example, we could say that 1 mole of hydrogen would have 6.022 times 10 to the 23 atoms of hydrogen. 1 mole of iron, for example, would have 6.022 times 10 to the 23 atoms of iron. So we could do it for anybody on the periodic table. We could use Avogadro's number as a relationship. And really, from either of those, we could write 2 conversion factors. We could write, for example, 1 mole of hydrogen over 6.022 times 10 to the 23 atoms. Or if we needed it the other way around, we could flip it around and put Avogadro's number there up on top, divided by 1 mole. So we can use it either way. It doesn't really matter which way you use it, depending on sort of the problem that you're looking at. Now, we can also use Avogadro's number not for just individual sort of atoms or elements from the periodic table, but we can use them in molecules or compounds. So, for example, if we had 1 mole of water, that would have 6.022 times 10 to the 23. And because water is not an element by itself, it is a molecule, we would use the units here of molecules of water. And just like below, we could use it as 2 conversion factors. We could use 1 mole of water over 6.022 times 10 to the 23 molecules, or 6.022 times 10 to the 23 molecules of water is 1 mole of water. So again, Avogadro's number doesn't change, but the units do change depending on sort of the application of how you're using it. So if you're using it for anything that's really a molecule or like a compound, you should use molecules as the units. If you're using it for anything that's really just like an element by itself from the periodic table, you should use the units of atoms. So that's why we look for really both of those words, either atoms or molecules, to know if we should use Avogadro's number, because you could use them for both. Any questions on that there? All right. So we talked about the question. Okay. Yep. So the other really important sort of conversion that we use a lot, and probably honestly more than what we use Avogadro's number for, is molar mass. So molar mass is really a big important conversion. Molar mass has 2 units associated with it. It is grams per mole are the units. So where do we get basically the molar mass? We get the molar mass actually from the same place that we get the atomic mass, and that is the periodic table. So when we look at, say, hydrogen, for example, we see 1.008 there on the bottom. If you remember, that is the atomic mass, which we talked about how to calculate the atomic mass, right? By isotopes and all that good stuff. And sometimes that is given in AMU, which is atomic mass unit. But if you've ever been to a balance or used the balance, you don't see AMU on your balance, you see grams. So a more convenient use of those numbers on the periodic table is to convert them to molar mass. And we do it basically the same way. The good news is the atomic mass in AMU and the molar mass in grams per mole are the exact same number. So they're numerically equal to each other. So for hydrogen, the molar mass would be 1.008 grams per mole. The number always stays with the grams part, and it's always 1 mole when you are asked to calculate the molar mass. So that is really something important to keep in mind. If you're asked to calculate the molar mass of something, you should do it based solely on the formula, just one formula by itself, regardless if it's maybe in an equation, there's a number in front of it, doesn't matter. You should only calculate the molar mass based off the one individual formula and how much is there. We could basically use molar mass as our conversion factor to go between grams to moles, which is something we do a lot, and go from moles back to grams. So really the periodic table and the molar mass is our conversion factor to do that. We can use it like a conversion factor. So for example, here again, we could put 1.008 grams per mole of hydrogen, or if we needed it the other way, a mole of hydrogen would be 1.008 grams. So again, dimensional analysis, we could really use it as a conversion factor. If you're asked what is the molar mass of hydrogen, this is usually the way that is reported, with the grams on top and the moles on the bottom there. And again, it's always 1 mole. We could do that for anybody on the periodic table. If we looked at carbon, it says 12.01. That means the molar mass of carbon is 12.01 grams per mole. That means for every mole of carbon, there is 12.01 grams. We could also do this for something that is a molecule or a compound. So if we had something like water, which is H2O, if we wanted the molar mass of water, we basically go to the periodic table, add up all the parts. So there are 2 hydrogens. Each hydrogen from the periodic table is 1.008 grams per mole. And there's 1 oxygen from the periodic table, which is 16. So that's basically our hydrogen, and that's our oxygen. And when you add that together, that gives you how many grams there are per mole. So that's 18.02 grams per mole of water. That means 1 mole of water would have 18.02 grams. Again, you could also use it as a conversion factor, grams on top, moles on the bottom, or flip it, moles on top and grams on the bottom as well. So you could do that as well here. So let's say we had C3H6 and we wanted the molar mass. What would it be? I'll give you some numbers in case you don't have a periodic table. 12.01 for carbon and hydrogen, which are the 2 I have on here already, I guess. I'll write it again. 1.008. All right, what would the molar mass of this guy be here? Okay, so once again, if we wanted the molar mass, we should roll to the periodic table. We should look at these numbers. And basically, the general rule is, depending on your periodic table, you usually will take 4 significant figures off of each of those numbers. So your periodic table may give you a bunch of numbers underneath each symbol, or may round, but usually speaking, molar mass is 4 significant figures. And when you calculate the molar mass, usually 4 significant figures is sort of where you lay up in terms of how much. So we're just going to add up all the parts. So we have 3 carbons. So each carbon is 12.01 from the periodic table. There are 6 hydrogens. Each one is 1.008. And that would get us a molar mass of, I hope, 4208 grams per mole here. And again, we could use that as a conversion factor of either there's 42.08 grams per mole of this guy, or in 1 mole, there is 42.08 grams. Any questions on that there? I would say, again, out of the 2, molar mass is definitely something that you use probably the most. And really, you want to think of these 2 things really as conversion factors. And again, make sure that if you are going to use Avogadro's number, you use it when you need to and not when you should not use it. So what is the relationship between kind of both of those things, Avogadro's number and sort of molar mass? So the relationship is this: if I had 1 mole of hydrogen, that would equal 1.008 grams of hydrogen. And that would also have 6.022 times 10 to the 23 atoms of hydrogen. Same thing with our water, and 1 mole of water, that would equal 18.02 grams of water, and that would have 6.022 times 10 to the 23 molecules of water. So that is the relationship between all 3 of those things. Because they're all a mole, they all have basically Avogadro's worth of atoms or molecules, but each mole is a different amount of grams, right? And that is why when we saw that picture a little bit earlier that I kind of jammed by, let's just go take a look at that, and I'll come back to this here in a sec. That is why when we look at this picture here, these are all 1 moles of each of these substances. But when we look in the beaker, are they all the same amount? They are not, because a mole of sulfur, for example, represents 3207 grams. A mole of carbon represents 12 grams, right? So although they're all still a mole of something, say gram-wise, they do represent a different amount of grams. So that's why, even though they're all still a mole of each of these substances, there's different amounts in there, just like a mole of water would be 1802 grams and so forth. All right, so again, you could use sort of this relationship here between these two. You could use this, which is the molar mass. And this is obviously Avogadro's number, and that is molar mass, those 2 relationships there. All right. So let's take a look at some examples here where we do some calculations using these. All right, let's try a couple here. Let's do both of these. All right, we want to know how many moles of helium are there in 5.46 grams of helium. Again, if you look up helium on the periodic table, 4.003 is the number you'll see underneath it. And zinc, how many grams of zinc are there in 0.25 moles of zinc? And if we look up zinc there on the periodic table, 6539 is what we see underneath it. All right, take a couple of moments here and see what you come up with. First one, we're looking for moles. Second one, we're looking for grams. Okay, let's take a look and see. So we'll start with the first one here. We're looking for moles. We have grams. So the first question is, should I use Avogadro's number here? Yeah, the answer is no, because there's no mention of atoms, there's no mention of molecules, so we do not want to use Avogadro's number. This is really a conversion between grams to moles. And remember, it's the periodic table and the molar mass that allows us to do that. So we would go to the periodic table, we would find helium, we would see that number, and that number basically means that there are 4.003 grams of helium in a mole, which is the molar mass of it. Or we could use it in the opposite direction as a conversion factor, mole on top, 4.003 grams on the bottom. So in this particular case here, we would start with our grams, which is 5.46 grams of helium. Remember, opposites cancel, so grams are on top. So in this case, we do want to use the conversion factor like this, where moles will end up on top, which is what we're looking for, 4.003 grams on the bottom. Grams would cancel, basically take 5.46 divided by 4.003, going to give us a 1.36 moles of helium. sig figs based off of that number right there. Any questions on that calculation there? Okay. Looking at the next one here, we want grams and we have moles to start with. So again, here we do not need Avogadro's number, no mention of atoms, no mention of molecules. This again is our moles to grams conversion, which once again is the periodic table and our molar mass that we're going to do it. So looking at zinc, that tells us there's 6539 grams of zinc in a mole. A mole is 65.39 grams. So in this case, we're starting with moles. So remember, we want opposites cancel. So we do need moles on the bottom, which means we're going to multiply by the molar mass in this case. So we would use that conversion factor there. The moles will cancel, and we'll take 0.256 times 6539, going to give us 16.7 grams of zinc, which again would be a more usable unit of like go measure out 0.256 moles of zinc. You would know you should go measure out 16.7 grams of it, right? Question on either of those two calculations. Those are very, very common calculations that are done a lot in chemistry. Yeah? Grams to moles, moles, grams. Any questions on either of those? All right, why don't you try the next one, which is we're looking for how many grams is one gold atom, I think is what you got next. So let's take a look at that. All right, so what is the mass in grams of one gold atom? If you go to gold on the periodic table, $1.97 looks like what you got going on there. All right, see what you come up with here. Avogadro's number here. The keyword there is atoms, which means Avogadro's number probably should be used somewhere along the way. Our path here is we're actually starting with atoms. So atoms using Avogadro's number will take us to moles, and then we would want to go moles to grams using the molar mass. So that's sort of the pathway to get us there. We know here we'll need the molar mass. So for gold is 197 grams per mole would be the molar mass. So starting with one gold atom here, we would then use Avogadro's number. So in this case, Avogadro's number would go on the bottom so that the atoms would cancel. And that's a mole of gold in this case. If I stop right here at this point, I'm in units of moles. I pretty much have got into here. So I do need to do the last conversion there to get me to grams. That is where our molar mass comes into play. Once again, I could clearly see from my dimensional analysis, moles are up on top, which means to cancel them, I do need to keep the moles on the bottom. And the 197 grams up on top so that the moles will cancel in this point. That's going to leave me just grams in terms of the units. And that would be basically 197 hit equals divided by Avogadro's number, making sure to use our exponent button. And that would get us something like 3.271 times 10 to the minus 22 grams of gold, which is technically what one gold atom weighs, kind of small in terms of its mass. Yeah. Any questions on that calculation there? All right, let's try one more and then we'll call it for today. All right, let's try, let's see this one. Let's do how many moles and molecules are there in 37.3 grams of C2H6O. So from the periodic table, some of the numbers, 12.01 for carbon, hydrogen 1.008, and oxygen being 16. All right, give that a go to wrap it up. Okay, let's take a look, see how you're doing. So in this case, we're looking for moles and molecules. So again, the key word there is molecules. So we do need to use Avogadro's number along the way, but we are also looking to get to moles. So our pathway here is we're starting with grams. So we could use the molar mass from the periodic table to go from grams to moles. Once we have it in moles, we then can use Avogadro's number to take it from moles to molecules in this case. So kind of a two-step process here. So to do that, we will need the molar mass of this compound. And to find the molar mass of the compound, we just go to periodic table. And once again, we're just going to add up all the parts that are there in the formula. And we're just going to use the formula, no other number, just what's in the formula to calculate that. So there are 2 carbons, each at 12.01 from the periodic table. There are 6 hydrogens, each at 1.008 from the periodic table, and 1 oxygen, which is 16 from the periodic table. That gives us a molar mass of this compound here of 4607 grams per mole. Remember, that's basically going to be our conversion factor to do the front part here of the calculation, take it from grams to moles. So that's where we'll start. We'll go with our 37.3 grams of our C2H6O. Using our molar mass as a conversion factor, grams are on top. So we do actually want to flip this around when we use it in the calculation. We want to put the grams on the bottom, which would be 4607. And we want the moles to end up on top here. That way the grams cancel. Any questions up to there? Since we actually do want an answer for moles, we should probably get an answer here. So I won't continue on at this moment. So we'll take 37.3, we'll divide it by 4607, and we'll end up with something like 0.810 here if we do a little bit of rounding. Moles of C2H6O. I went to 3 significant figures really based off of that original number there. Yeah. Any questions on that there? So with that first calculation, it took us basically to here, or here. So we do want to get to molecules now. So this is where our Avogadro's number is going to come into play. So I'll just use the rounded number here since I have it. And remember that in this case, 1 mole of anything, in this case of C2H6O, will equal Avogadro's number, which should go up on top, as those are molecules of C2H6O. My parentheses can't hold it, apparently. And that is going to get rid of our moles. And we will end up with, I'll use the rounded number here, 6.022. Make sure you hit your exponent button and 23. And that would get us something like 4.88 times 10 to the 23 molecules here of C2H6O in this case. Yeah. So those are both of the answers here. Any questions on any part of that? Grams to moles, moles, grams, molecules, Avogadro's number. Questions? Okay, we're laid up there